Okay. So hopefully you've already written this down. You can see it's a problem. All we want to do is find the reactions. Now this problem I didn't spell out exactly what the reactions are. If you look in the book and find a problem similar to this, the author will tell you that at A, this connection looks like a pin, and it is. And over here at B, you can see it's just a roller setup. So this will be a roller, and this will be a pin. That's usually typical that field to find that. So the first thing I like to do is just draw the free body diagram for the structure. So I'll start with the geometry. So I'll replace the beam with a line that has the same length. And then I'm going to decide how I'm going to model this reaction or this support condition at A. Now we know it's a pin, so what is a pin? How many unknowns at a pin? Yeah, we've been counting these up for our determinacy problems. There's 2. Now, I uniformly, without really thinking, always assume that my Y component acts up and my X component acts to the right. And I do that simply because those correspond to the typical Cartesian coordinate system. Up's usually positive, to the right's usually positive. And I don't really think about it. I'm not trying to look at the problem and analyze whether my reactions are going to go up or down. You can if you like, but I think that's lost energy in terms of solving the problem, trying to predict some stuff. Now later we can use that intuition to see if you got the right answer. So now when I go over here to B, B does not have a horizontal component, so I'll simply just assume that it has a component vertical. Again, it'll be up. I'll just call that dy. So that's my first thing. I decide what I'm replacing. So my original system had supports, and now I'm removing them and replacing them with equivalent set of forces that model those supports. Now what else is happening on this beam? Well, I've got a force in the middle. That's 24 kilonewtons. And then what else? Well, I've got a distributed force on the end. Now we don't usually deal with the distributed force in this condition. What do? We find a concentrated force that's equivalent to it. And all it has to do is the area under the curve is the force, and it acts through the centroid of that area. Well, this is easy. It's a rectangle, right? Area of a rectangle is base times height. So that's 3 meters times 2 kilonewtons per meter. That's 6 kilonewtons. And I'll draw that with a double line. I'll try to do that throughout the course, indicating that that's not the real force. That's an equivalent force of this. And since it's going to act in the middle of 3 meters is 1.5 meters, and I'll just write that on the end here. So that's my 1.5 meters to there. So I've got 6 meters, 6 meters, and these little 1.5 meter segments. Now for this problem, and I think for us in the class, that's a pretty complete free body diagram. It communicates a lot of stuff. I've got geometry. I've got my assumption for the reactions. I've got indicated that I've got an equivalent load. And now all I have to do is what? Apply my equations of equilibrium. Now the strategy I just talked about a minute ago, this would be a good time for this to come into play. I suggested that you always sum moments first. So where would be a good place to sum moments? Would it be a good place to sum moments right here in the middle? Now why would that be a terrible place? Yeah, because AY and BY would both create moment about that point. AX would not, so that's not good. One equation, 2 unknowns, that's not good. How about at B?
Good.
B would work in this problem because BY passes through B, and also for this problem, AX passes through B. So I could get one equation and one unknown, AY. But I think if you want to save time and be efficient, always go for the pin. So that's what I'm going to do. I'm going to sum moments about A. I'm also going to indicate that I'm going to use right-hand rule for my sign convention. And I'm going to say I'm going to sum moments at A, make equal 0. Now, this is a pretty powerful statement symbolically. It says first I'm summing moments at A, and it's in equilibrium. That's pretty important. And I'm also indicating what I'm assuming is positive moment. you can assume whatever you want. It doesn't really matter. It's either going to be clockwise or counterclockwise, one or the other. I use right-hand rule because that's the traditional sign convention, so I'll do that. So when I sum moments about A, and I'm looking at this force 24 kilonewtons, what kind of moment does it create about A? Is it going to be a positive moment or a negative moment with right-hand rule? It's going to be negative. So I'm going to start with the negative sign, indicating that what I'm about to compute is going to be a negative moment. And of course, moment is force times distance. The force would be 24 kilonewtons. And the distance from A to that is 6 meters. Now, a lot of students look at this and say, oh, that's negative because the force is acting down. That's not true. The force is acting down. That is true. But it's not a negative force in this sense. That negative is attached to the moment. Right? If I sum moments at B, what would that moment be? It would be positive. Have the same exact value, but it would be a positive sign. So keep that in mind. So now I'm looking at A. What other forces do I have? I have this 6 kilonewton force. Is that positive or negative moment? It's going to be negative. The force is going to be 6 kilonewtons. And the moment arm is going to be the distance from A to the centroid, which looks like 6 plus 6 plus 1.5. That's 13.5 meters. What else is that creating a moment about A?
BY.
Yeah, BY. Now, what kind of moment is that about A with right-hand rule sign convention? Becomes positive. So it's a positive moment. The force is BY. The distance from A to B is 12. I'm taking my time and going really slow and explaining everything because I just kind of give you a strategy, I think, that if you apply consistently, you're probably less likely to make a mistake, especially in the pressure of the exam. So what's BY equal to? Somebody solve that for me.
18.75.
Anybody else get 18.75? Yep. Positive?
Yep.
Okay, see, now I suggest that you look at this and you decide, does that make sense to you? Okay, I got a positive answer, which means I assume the right direction for BY. Does it make sense that BY is up? And I say, yeah, all your forces are down. Probably both your reactions in this case are going to be up. That seems reasonable. It's not a clear check. Oh, yeah, 18.75 is correct. At least it gives you some insight. And later in the course, whether this is positive or negative and how the structure behaves will give you some feedback that you're going in the right direction. Okay, now with BY done, I can sum forces X, sum forces Y. Does either one of those afford any kind of advantage to do first? Sum forces in X is going to be the easiest one, right? I'm going to come in here and say, hey, I'm going to assume right is positive, and I'm going to sum all the forces in the X direction and make sure they're in equilibrium. So just like I made my statement here about equilibrium, I'm making one here about X. And looking at this system, what are the forces in the X direction? There's only AX. So AX is 0. That was an easy one. So now I don't have any choice. I'm down to my last equation. I'm going to assume up is positive, and I'm going to sum all the forces in the Y direction. Make sure that's in equilibrium. So there's my kind of statement for that. So let's sum them all up. So I'm going to start from the left and work to the right. My two unknowns are going to be AY acting up. That's positive. BY is acting up. That's positive. Now, if I'd assume positive is down, those would have both been negative forces. So once you make an assumption on your sign convention, just stick with it. Now, 24 and 6 kilonewtons are positive or negative forces in this sign. Negative. So I've got 24 kilonewtons minus 6 kilonewtons. Now I can take my value for BY and put it right in there. Another reason why you should never go back and mess with your free body diagram is, what if BY were negative? What do you plug in here for BY? You plug in the negative value, and it will take care of itself. Right? You don't run back over here and try to change this and then rewrite this expression to the new diagram. Just leave it alone. The only time you should change your free body diagram is if you just made an error. Right? Go back, get it cleaned up, then write your equations again. Don't change it midstream. So this would be pretty easy. What's AY going to be? 11.25. Everybody else get that? You probably wish you'd gotten this one for mastering engineering, huh? So there you go. Pretty simple problem just to get started. Any questions about that? Okay. Excellent.